let's discuss the continuity of the function f of x. As you know that this is a piecewise function, and on the interval from negative infinity to 0, you have irrational functions. And on the interval from 0 to positive infinity, you have a linear equation, a linear function. Now you are asked to determine on which intervals the function f of x is continuous. And since f of x is comprised by two subfunctions, we want to look at the continuity of each of the function on its domain. From negative infinity to 0 first. We have irrational functions, and the denominator is a factor of x minus 5 and x plus 4. So then we know that the function is discontinuous at x equals to 5 and x equals to negative 4. Right? So at x equal to negative 4, the function is discontinuous. What about when x equal to 5? It doesn't matter because this rational functions here is only defined on this interval from negative infinity to positive to 0. So 5 is on the other side, which doesn't matter in this example. Okay. How about from the interval on the domain from 0 to positive infinity? We have a linear equation 3x plus 6, and you know that linear equation is defined everywhere. So we don't have to worry about the discontinuity on the domain from 0 to infinity. Okay. One more thing, that because it's a piecewise function, so this always could be the point where the graph is connected. Could be a problem there. So you have to evaluate the point where x equal to 0 to see is it continuous here or not. And how can we determine whether the function is continuous at 0 or not? So remember that for a function to be continuous as a point, we have to make sure that the function is satisfying the three conditions. So the first condition is f of 0 is defined. The second is the limit of the functions when x goes to 0 exists. And the third one is the function value at 0 is the same as the limit when x goes to 0. Well, the first conditions, we, since 0 is defined here, so then we plug 0 into this function to see if we can get a value. And 0 is fine, right? Place 0 in here, 0 in here, 0 here, 0 here, 0 here, and you will get negative 25 over 24. So yes, the function is defined here. What about the limit when x goes to 0? Remember that in order to determine this limit, we have to evaluate the limit from the left and the limit from the right at this point, x equal to 0. Let's go here. The limit of the functions when x goes to 0 from the left is going to be the function value when x equal to 0, right? As from the left, you use the rational functions. So you plug 0 in here, it's approaching to negative 24, 5 over 24. What about the limit of the functions when x goes to 0 from the right? From the right, you're going to use this functions, the linear equations here. And you plug 0 in here, it's approaching to 0, which is, and you plug 0 in here, you get 6. So then now, we can just, and then you see that this value and this value are not the same, so that means the limit doesn't exist. It's violated one of the conditions. That means at x equals to 0, the function is discontinuous. So far we found, let's say find the discontinuities. So we find the discontinuities x equals to 4, right? Because if you plug 4 into this functions, is undefined. And the second point that we found is 0. Okay. And then using the discontinuities, we can determine the intervals on which the function is continuous. Negative infinity to 4, union to, you gotta go from smaller to larger value, which is negative 4. So it should be negative 4, and so negative 4, union to negative 4 to 0, and union to 0 to positive infinity. So these are the three intervals on which the function is continuous. As you can see that we used the discontinuity point to find these intervals. All right. Well, we want to classify the discontinuity, the three types, removable, jump, or infinite. So when x equals to 4, x equals to negative 4 is one of the discontinuities. If you plug negative 4 in here, you have, and since negative 4 is a vertical asymptote, because if you plug negative 4 into these functions, you get 0. So since it's a vertical asymptote. If it's a vertical asymptote, then it has to be an infinite discontinuity. When x equal to 0 is another discontinuity, and we found that the limits from the left and the right are not the same, so you have a jump from the left to the right, from negative 25 over 20, this should be 20. Negative 25 times divided by negative 5 times 4, so you should have negative, wow, my arithmetic is not right here, so negative 20, negative 20. Okay, so it's from a value the different, so you jump from negative 25 to over negative 20 to 6. Then at 0 at the connecting point, you have a jump discontinuity. All right. And then the next question is, at each discontinuity, determine whether is its left, right, continuous, or neither. So again, when x equals to negative 4, is a vertical asymptote. So for example, if the function looks like this, then you don't have, like, it's an f at negative 4, the function at negative 4 is undefined, right? Then you would have neither left or right discontinuity. Neither left or right continuous at x equal to negative 4. And when x equal to 0, well, you have the function is defined as x f of 0, which is negative 25 over negative 24. I can reduce this to 5 over 4. So f of 0 is 5 over 4. And the limit x goes to 0 from the left is also 5 over 4, which is the same values. So by the definitions, we can conclude that at this point the function is left continuous. And we can make these conclusions based on the domain of this piecewise functions. Because look at 0 right here. You have 0, right? And then you have like the bracket because it's included 0 on the left side, and you have the parentheses because it's not included 0 on the right side of 0. Then you know that the function is continuous up to this point. So then you know that it just have to be left continuous. At x equal to 0. Alright, so this is an example on how to discuss the discontinuity of f of x.